Tonight, we're going to confront a question that sounds like science fiction, but is actually one of the hardest engineering and survival problems humanity has ever seriously studied. A generation ship. A vessel designed to carry thousands of people across the void between stars on a journey lasting centuries or even millennia. But here's what almost nobody talks about. The hardest part isn't building the engine. It isn't reaching the right speed. The hardest part is keeping everyone alive long enough to arrive. Because a generation ship doesn't just need to cross space, it needs to be a self-sustaining world, a closed civilization hurtling through absolute darkness with no resupply, no rescue, and no margin for the kind of failures that would be routine anywhere else. And the question of how long it can actually last has answers that are deeply unsettling. Before we dive in, if you find these kinds of deep explorations fascinating, a quick like or subscribe would genuinely help this channel keep going. It's a small thing for you, but it makes a huge difference for me. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, let's begin. Let's start with a question that seems straightforward but isn't. How do you get humans to another star? Not a robot, not a radio signal. Living, breathing human beings, standing on a planet orbiting a star that isn't our sun. The distances involved are the first thing you need to understand, because they set up the entire problem. The nearest star system to us is Alpha Centauri, about 4.25 light years away. A light year is the distance light travels in 1 year, moving at about 300,000 kilometers per second. So 4.25 light years is roughly 40 trillion kilometers. That's 40 with 12 zeros after it. To put that in perspective, if you could somehow drive a car at highway speed, about 100 kilometers per hour, non-stop, day and night, without ever stopping for fuel or rest, it would take you roughly 45 million years to reach Alpha Centauri. The fastest spacecraft humans have ever built, the Parker Solar Probe, reaches speeds of about 192 kilometers per second when it's closest to the sun. Even at that speed, which is about 17 times faster than the Apollo spacecraft that took astronauts to the moon, it would still take roughly 6,800 years to reach the nearest star. And the Parker Solar Probe is a small, lightweight instrument package. It's not carrying a crew, a habitat, food, water, air, or any of the other things humans need to survive. A crewed spacecraft capable of sustaining people would be far heavier, and getting a heavier object to those kinds of speeds requires exponentially more energy. The engineering reality is this: with any propulsion technology that is grounded in known physics, not warp drives, not wormholes, not anything speculative, but real technology we can plausibly build or envision building within the next century or two. A crewed spacecraft heading for another star would likely travel at somewhere between 1% and 10% of the speed of light. At 1% of light speed, which is about 3,000 kilometers per second, the trip to Alpha Centauri takes roughly 425 years. At 10% of light speed, it takes about 42 years. 42 years is a long time, but it's within a single human lifetime. So if we could build a ship that reaches 10% of light speed, we might be able to send a crew that arrives alive without needing multiple generations. But here's the problem. Getting a large crewed spacecraft to 10% of light speed is extraordinarily difficult. The energy requirements are staggering. You need to accelerate not just the crew, but the entire ship, all its life support, all its supplies, all its structure to that speed. And then you need to slow it down again at the other end. The amount of fuel required depends on the type of propulsion, but for most realistic designs, the mass of fuel needed dwarfs the mass of the ship by orders of magnitude. A ship that weighs 10,000 tons might need millions of tons of fuel just to reach a few percent of light speed. This is why many serious studies of interstellar travel keep coming back to the same conclusion. For any reasonably large crewed vessel with a propulsion system grounded in known physics, the travel time to even the nearest stars is likely measured in centuries, not decades. And once you're talking about centuries, you're talking about a journey that no single human being can complete within their own lifetime. The people who board the ship will not be the people who arrive. Their children won't be the people who arrive. Their grandchildren might not be the people who arrive. The destination will be reached by people who have never known anything other than the inside of this vessel. People born on the ship, raised on the ship, and who will live out most or all of their lives on the ship. This is a generation ship. Not a transport vehicle, but a world. A sealed, moving habitat where human beings live, reproduce, raise families, educate their children, grow old, and die, all while the ship drifts through the emptiness between stars. The concept has existed in science fiction for over a century, but it's also been studied seriously by physicists, engineers, biologists, and social scientists. And the conclusions from those studies are sobering, because a generation ship doesn't just face one problem. It faces dozens of problems, all of them interacting, all of them accumulating over time, and any one of them capable of ending the mission permanently. But before we get to those problems, you need to picture what this ship actually looks like. Because the physical reality of a generation ship is something most people have never thought through, and understanding the vessel itself is essential to understanding why everything that can go wrong eventually does. A generation ship is not a spacecraft in any conventional sense. It's not a capsule, it's not a shuttle, it's not even something like the International Space Station, which is a collection of modules about the size of a football field. A generation ship would be one of the largest structures ever built by human hands. It would need to be, because it must contain everything a human civilization needs to survive indefinitely. Housing for thousands of people, agricultural zones large enough to grow food for all of them, water reservoirs, treatment facilities and distribution networks, air processing systems, power generation, manufacturing capability, medical facilities, schools, storage, waste processing, recreation areas to maintain psychological health, and enough structural mass to provide some degree of radiation shielding. Serious engineering studies have estimated that a generation ship capable of supporting roughly 5,000 to 10,000 people would need to have a total mass in the range of millions of tons. Some proposals go even higher, into the tens of millions of tons. For comparison, the International Space Station has a mass of about 420 tons. A generation ship would be roughly 10,000 to 100,000 times more massive. This is not an incremental step beyond what we've built before. It's a leap of several orders of magnitude. The habitable volume is just as staggering. If you give each person a living space equivalent to a modest apartment, plus shared spaces for work, agriculture, recreation, and infrastructure, you need somewhere between 50 and 100 cubic meters per person at a bare minimum. For 5,000 people, That's 250,000 to 500,000 cubic meters of pressurized, climate-controlled, atmospherically managed interior space. In practice, the agricultural areas alone could dwarf the living quarters, because growing enough food for thousands of people requires an enormous amount of cultivated area. Estimates vary, but a rough figure is somewhere between 50 and 200 square meters of intensive agricultural space per person, depending on the crop types, the efficiency of the growing systems, and whether animal protein is part of the diet. For 5,000 people, that's 250,000 to 1,000,000 square meters of farmland inside a spaceship. That is the scale of the problem. Then there's gravity. Humans evolved under Earth's gravitational pull of 1G. Our bones, muscles, cardiovascular system, vestibular system, and fluid regulation are all calibrated for this specific gravitational environment. In microgravity, as we've learned from decades of research aboard the International Space Station, the human body deteriorates. Bone density drops at a rate of roughly 1 to 2% per month. Muscles atrophy. The heart weakens because it doesn't have to pump against gravity. Fluid shifts toward the head, increasing intracranial pressure and causing vision problems. The immune system behaves differently. For a journey lasting centuries, microgravity is not an option. The crew must live in something close to Earth normal gravity, or their bodies will degrade within a single generation, and their children may develop in ways that make them fundamentally unable to function on a planet at the end of the journey. The most widely studied solution is rotation. If you spin a large structure, the centripetal acceleration experienced by objects on the inner surface of the outer wall mimics gravity. This is real physics. It works. But the details matter enormously. The apparent gravity depends on two things: the radius of rotation and the rotation rate. A smaller radius requires a faster spin to produce the same gravity, but faster spin creates a stronger Coriolis effect. The Coriolis effect is the apparent deflection of moving objects inside a rotating reference frame. If you drop a ball inside a rapidly spinning habitat, it doesn't fall straight down. It curves. If you walk in one direction, you feel slightly heavier. Walk the other way, you feel slightly lighter. Throw something and it veers off course. The inner ear, which governs your sense of balance, can become confused, leading to chronic motion sickness. Studies of human tolerance to rotating environments suggest that the rotation rate should be kept below about 2 revolutions per minute to avoid severe discomfort, and ideally below 1 revolution per minute for long-term habitation. At 2 revolutions per minute, you need a radius of at least about 224 meters to produce 1G of apparent gravity. At 1 revolution per minute, you need a radius of about 894 meters. That means the rotating section of the ship needs to be roughly 450 meters to nearly 1,800 meters in diameter. That's a structure between 1,500 and 6,000 feet across. Rotating in space for centuries. The structural engineering required to build and maintain a rotating cylinder of that size, under continuous centripetal loading for hundreds of years, is beyond anything humanity has ever attempted. The stresses on the structural members would be constant and unrelenting. Every weld, every joint, every beam would be under load every second of every day for the entire voyage. This is where the engineering challenges we'll discuss later become particularly acute, because structural fatigue in a rotating habitat isn't just a maintenance problem. It's a survival problem. If a primary structural member fails in a rotating section, the consequences could be catastrophic. Loss of atmospheric integrity, loss of gravity, loss of everything. The energy budget adds another layer of complexity. A generation ship needs power for everything: lighting the agricultural bays, running the water recycling systems, operating the air scrubbers, powering the computers and communication systems, running the manufacturing equipment, heating the habitat, and doing all of this continuously without interruption for centuries. The most plausible power source is nuclear, either fission or, if the technology matures, fusion. A fission reactor could theoretically operate for decades on a single fuel load, but it requires uranium or plutonium, which must be carried aboard. The fuel is finite. Reactors also produce radioactive waste that must be managed and stored safely inside the ship. Reactor components degrade under radiation bombardment and require maintenance and eventual replacement. A fusion reactor, if it could be made to work reliably, would use hydrogen or helium isotopes as fuel, which are more abundant and produce less problematic waste. But sustained, reliable fusion power remains an unsolved engineering problem as of today. Whatever the power source, the ship needs redundancy. If the primary reactor fails, there must be a backup, and ideally a backup to the backup. Loss of power on a generation ship is not a blackout. It's a death sentence. Without power, the lights go out, the plants die, the air stops being recycled, the water stops being purified, the temperature drops or climbs to lethal levels, and the entire ecosystem collapses within days or weeks. The total energy demand of a generation ship supporting 5,000 people has been estimated at somewhere between 100 megawatts and several gigawatts, depending on the design, the efficiency of the systems, and the size of the agricultural operation. For reference, a large modern nuclear power plant produces roughly 1 gigawatt. So a generation ship might need the equivalent of one to several full-scale nuclear power plants, running continuously, maintained by the ship's crew, using fuel and materials carried on board, for the entire duration of the voyage. And the reactors themselves are subject to the same degradation and maintenance challenges as every other engineering system on the ship. This is the physical reality of a generation ship. It's not a sleek vessel gliding gracefully between the stars. It's a massive, rotating industrial facility, a small city wrapped in a cylinder, carrying its own power grid, its own farms, its own factories, its own hospitals, its own schools, and its own government. It must function as a completely self-contained world, producing everything it needs from a finite stockpile of resources, maintained by a small population that must remain skilled, motivated, and cooperative for longer than most civilizations on Earth have existed. And the first and most fundamental threat to this world is the problem of life support. To understand why this is so difficult, you need to understand what life support actually means on a generation ship. On Earth, you don't think about life support. The planet provides it automatically. The atmosphere is maintained by photosynthetic organisms, plants, algae, cyanobacteria that absorb carbon dioxide and release oxygen. The water cycle purifies and redistributes water through evaporation, condensation, and precipitation. Soil microbes break down waste and dead organic matter, recycling nutrients back into the food chain. The entire biosphere, all of it, every forest, every ocean, every square meter of soil, teeming with microorganisms, works together as an integrated system that has been running and self-correcting for billions of years. And it's powered by an external energy source, the sun, which delivers about 1,360 watts of energy per square meter to the top of Earth's atmosphere, continuously, for free, and has been doing so for 4.5 billion years. A generation ship has none of this. It has no sun shining on it providing free energy. Whatever energy it uses must come from an onboard source, most likely a nuclear reactor, possibly fusion if that technology matures, or some form of stored energy. The ship is sealed. There is no outside air. There is no rain cycle. There is no vast ocean to buffer temperature changes. There is no soil ecosystem that has evolved over millennia to efficiently break down waste. Everything the crew needs to survive, every molecule of oxygen they breathe, every liter of water they drink, every calorie of food they consume, must be produced, processed, and recycled inside the ship. And it must be done perfectly, or at least close to perfectly, for centuries. Let me walk you through what that means in practical terms. A human being going about a normal day consumes about 550 liters of oxygen on average. During sustained physical labor, this increases to about 800 liters or more. A crew of, say, 5,000 people, which is toward the lower end of what population geneticists consider viable for a multi-century mission, would consume roughly 2,750,000 liters of oxygen every single day. That oxygen must be continuously regenerated from the carbon dioxide the crew exhales. On Earth, plants and other photosynthetic organisms handle this effortlessly, because there are trillions of them spread across the entire planetary surface, backed by an atmosphere containing about 1.2 quadrillion tons of oxygen, which is a massive buffer. If plant productivity dips temporarily, the atmospheric oxygen level barely changes because the existing oxygen reservoir is so enormous. On a generation ship, there is no such buffer. The total volume of atmosphere inside the ship is finite and comparatively tiny. If the oxygen regeneration system underperforms, even slightly, even for a short time, the crew notices. Carbon dioxide builds up, oxygen drops, people get headaches, then confused, then unconscious. If the problem isn't corrected quickly, they die. This means the biological or chemical systems responsible for converting carbon dioxide back into oxygen must run continuously, reliably, and at a steady rate that precisely matches the crew's consumption. Any disruption, whether from a mechanical failure, a disease affecting the plants, a change in lighting, a nutrient deficiency in the growing medium, a microbial contamination, anything, creates an immediate threat to survival. Now, oxygen is only one piece, water is another. A human needs about 2 to 3 liters of drinking water per day, but total water usage, including sanitation, food preparation, and industrial processes, is much higher. Even on the International Space Station, which is the closest analog we have to a closed habitat in space, the water recovery system processes about 9 liters of water per crew member per day. And the International Space Station only has a crew of about 6 to 7 people. Scale that to 5,000 people, and you need to process and recycle roughly 45,000 liters of water per day, every single day, for centuries. The water cycle on the ship must capture every drop. Humidity from the air, urine, sweat, wastewater from food preparation, runoff from agricultural areas, condensation from surfaces. All of it must be collected, filtered, purified, and redistributed. On Earth, this happens naturally across an entire planet with oceans, rivers, aquifers, clouds, and rain. On a ship, it happens inside pipes, filters, membranes, and treatment systems that must be maintained and repaired continuously. A failure in the water recycling system doesn't just mean inconvenience, it means contaminated water, which means disease, which means medical emergencies, which means additional strain on every other system. Then there's food. Feeding 5,000 people requires a substantial agricultural system, not freeze-dried rations or MREs. Those are finite supplies that will be consumed and gone. A generation ship needs continuous food production, growing crops, and possibly raising animals, fish, or insects for protein inside the ship using artificial light or directed sunlight, hydroponics or soil-based agriculture, and a nutrient recycling system that converts waste back into fertilizer. This is vastly more complex than it sounds. Agriculture on Earth depends on an intricate web of organisms. Soil bacteria break down organic matter and make nutrients available to plant roots. Mycorrhizal fungi form symbiotic networks with plants, helping them absorb water and minerals. Earthworms aerate the soil. Pollinators like bees and butterflies fertilize flowering crops. Predatory insects keep pest populations in check. Each of these organisms plays a role. Remove one, and the system can degrade. On a generation ship, you'd either need to replicate this entire ecological web in miniature, maintaining stable populations of hundreds of species of microorganisms, insects, and possibly larger animals, or you'd need to replace their functions with engineered systems, chemical fertilizers, artificial pollination, mechanical pest control. Both approaches are fraught with difficulty. Biological systems are complex and unpredictable. Engineered systems require maintenance and spare parts. And this brings us to the most sobering data point we have on the subject: Biosphere 2. In 1991, 8 people were sealed inside Biosphere 2, a 3.14-acre enclosed ecological facility in the Arizona desert. It was the most ambitious closed ecosystem experiment ever attempted. The structure contained multiple biomes, a rainforest, an ocean with a coral reef, a mangrove wetland, a savanna, a fog desert, and an agricultural area designed to feed the crew. It was sealed from the outside atmosphere. The goal was to demonstrate that a closed ecological system could sustain human life for 2 years. It didn't work, not entirely. Within the first 16 months, oxygen levels dropped from 21%, which is normal for Earth's atmosphere, to 14.5%. That's equivalent to the oxygen level at an altitude of about 4,200 meters, similar to many high mountain passes. The crew experienced chronic fatigue, impaired cognitive function, and difficulty performing basic tasks. They were essentially living at altitude sickness levels inside a building in the Arizona desert. The cause was traced primarily to microorganisms in the soil. Bacteria were consuming organic matter and producing carbon dioxide at rates the designers hadn't anticipated. The concrete structure of the facility was also absorbing carbon dioxide and chemically reacting with it, which meant the carbon dioxide wasn't available for plants to convert back to oxygen. The carbon cycle, the fundamental loop that was supposed to keep the air breathable, was out of balance. Oxygen had to be injected from outside, breaking the closure. But the problems didn't stop there. Most of the pollinating insects died. Several vertebrate species went extinct inside the enclosure. Cockroaches and a species of crazy ant exploded in population, overrunning parts of the habitat. Many of the crop species failed. Morning glory vines grew uncontrollably, smothering other plants. The crew supplemented their diet with seed stock that is supposed to be reserved for the second year. Interpersonal conflicts became severe, with the crew eventually splitting into two factions that barely spoke to each other. And this was a facility on Earth's surface with sunlight streaming through glass, with normal gravity, with the ability to pump in emergency oxygen if things got bad, with engineers and scientists on the outside monitoring everything, with the option to simply open the doors and walk out if someone was dying. A generation ship has none of those safety nets. There's no outside air to pump in. There is no team of engineers standing by just beyond the walls. There are no doors to open. If the oxygen drops, if the crops fail, if the water becomes contaminated, the crew must fix the problem themselves using only the resources that exist inside the ship. And if they can't fix it, they die. Every single person on board. The lesson of Biosphere 2 isn't that closed ecosystems are impossible. It's that they are extraordinarily fragile, and that our understanding of how to maintain them is still primitive. Biosphere 2 was the best effort humanity has ever made, supported by serious funding, serious science, and serious engineering, and it couldn't keep 8 people alive in a sealed environment for 2 years without outside intervention. A generation ship would need to keep thousands alive for centuries. The International Space Station provides another useful reference point, but it also highlights the limitations. The International Space Station has been continuously occupied since the year 2000. Its life support systems are sophisticated, recycling about 90% of the crew's water and generating some oxygen through electrolysis, splitting water into hydrogen and oxygen using electricity. But the International Space Station is not a closed system. It receives regular resupply missions carrying food, water, spare parts, and other consumables. On average, several tons of supplies are delivered every few months. The station also vents waste gases and relies on consumable chemicals for some of its air scrubbing functions. If resupply stopped, the International Space Station's crew would need to be evacuated within weeks. The life support system cannot sustain the crew indefinitely on its own. It's designed to reduce the amount of resupply needed, not to eliminate it. A generation ship can't be resupplied. Once it leaves the solar system, it is on its own. There are no supply ships. There are no emergency deliveries. There is nothing between stars, no asteroids to mine, no gas clouds to scoop, no stations to dock at. Interstellar space is the emptiest environment imaginable. The density of matter in interstellar space is roughly 1 atom per cubic centimeter. For comparison, the air in the room you're sitting in right now contains about 25 quintillion molecules per cubic centimeter. Interstellar space is a vacuum so complete that it makes the best laboratory vacuums on Earth seem crowded by comparison. This means that a generation ship must achieve what no human technology has ever achieved. A truly closed-loop life support system, one that recycles everything, wastes nothing, and runs without significant external inputs for hundreds of years. And it must do this while supporting not just a crew, but an ecosystem, the plants, microorganisms, insects, and possibly animals that make the food production and atmospheric recycling possible. This ecosystem must remain stable across extreme timescales. And here's the terrifying part. Ecosystems don't like being small. This is one of the most well-established principles in ecology. The smaller an ecosystem, the less resilient it is. Larger ecosystems have more species, more genetic diversity within those species, more redundancy, and more capacity to absorb shocks. A forest can lose one tree species to disease and the other species fill the gap. A small greenhouse loses one crop species and dinner is gone. This principle, sometimes called the species area relationship, has been documented across thousands of studies. It tells us that the smaller and more isolated an ecosystem is, the faster species go extinct within it, and the more vulnerable the whole system becomes to cascading collapse. A generation ship's ecosystem would be the smallest, most isolated ecosystem in the history of life. Smaller than any island, smaller than any lake, smaller than Biosphere 2 in terms of the number of species it could practically support and the physical area available. And it would need to persist for far longer than any small ecosystem has ever been observed to persist without external inputs. The risks of cascading failure are severe. Imagine a scenario where a fungal blight strikes the ship's primary grain crop. On Earth, this would be bad but manageable. You'd import grain from unaffected regions. You'd plant a different variety next season. You'd draw on strategic grain reserves. On a generation ship, there are no unaffected regions. There is no import. If the blight spreads to the backup crop varieties, and in a small enclosed environment with limited genetic diversity among crops, this is plausible, then food production drops sharply. Caloric intake falls. The crew becomes weaker, more susceptible to illness, less able to perform the physical labor required to maintain the ship. Stressed and hungry people make worse decisions. Social tensions rise. Meanwhile, the loss of plant biomass reduces oxygen production. Carbon dioxide rises. Air quality drops. The crew is now dealing with a food crisis and an atmospheric crisis simultaneously, both caused by the same root event. And they must solve both problems using only the tools, seeds, and knowledge that exist inside the ship. There is no calling for help. There is no outside expertise to consult in real time. Any communication with Earth, assuming they're still in radio range, has a delay of years or decades in each direction. By the time Earth hears about the crisis, it may already be over, one way or another. The closed-loop ecosystem of a generation ship is the single most critical system on board. If it fails, everything fails, and maintaining it requires a level of ecological understanding, agricultural skill, and biological monitoring that is significantly beyond what we currently possess. We are still learning how ecosystems work on Earth, where we have billions of years of evolutionary fine-tuning to study. Designing a synthetic ecosystem that can run reliably in a sealed container for centuries is a problem we don't yet know how to solve. This isn't a reason to give up. It's a reason to understand the magnitude of the challenge, because the life support system is only the first layer of the problem. Beneath it, around it, threaded through every wall and conduit and mechanical joint of the ship, there are other threats accumulating silently. Threats that have nothing to do with biology and everything to do with physics, material science, and the relentless grinding passage of time. And those threats are just as capable of ending the mission as a failed wheat harvest. But they work differently. They're slower, quieter, and in many ways harder to fight. Because you can replant a crop, you can breed new insects, you can adjust the chemistry of your water supply, but you can't argue with the laws of thermodynamics. You can't negotiate with metal fatigue, and you can't outrun the slow, patient decay of every material object ever built by human hands. That's the next layer of the problem, and it's one that most people never think about when they imagine a ship sailing between the stars. On Earth, you are shielded from the universe, Most people never think about this because the shielding is invisible. You can't see it, you can't feel it, but it's there, every second of your life, and without it, you would be dead. Earth's magnetic field extends tens of thousands of kilometers into space, forming a vast protective bubble called the magnetosphere. This field deflects the majority of charged particles streaming from the sun and from deep space, funneling them toward the poles where they produce the auroras. Beyond the magnetic field, there's the atmosphere itself. You're sitting at the bottom of an ocean of air, roughly 100 kilometers deep. That air, all 5 quadrillion tons of it, acts as a radiation shield. The atmosphere provides shielding equivalent to roughly 1,000 grams per square centimeter of material overhead. That's equivalent to about 10 meters of water sitting above you in every direction. This is an enormously effective shield. High-energy particles from space slam into atmospheric molecules high above the ground, creating cascades of secondary particles that are mostly absorbed before they reach the surface. By the time cosmic radiation reaches sea level, it has been reduced to a small fraction of what exists in open space. You receive a radiation dose from cosmic rays at sea level of roughly 0.3 millisieverts per year. That's almost nothing. Your body can handle it easily. Now remove all of that. Remove the magnetic field, remove the atmosphere, remove the planet itself, put a human being in a metal container drifting through interstellar space, and the radiation environment changes completely. In deep space, between the stars, the dominant radiation threat comes from galactic cosmic rays. These are not ordinary particles. Galactic cosmic rays are atomic nuclei, mostly protons, but also heavier elements like helium, carbon, oxygen, silicon, and iron that have been accelerated to extraordinary energies by supernova explosions, neutron stars, and other violent astrophysical events. Some galactic cosmic ray particles carry energies of billions or even trillions of electron volts. At these energies, a single particle can punch through meters of solid material, breaking apart atoms along its path and leaving a trail of ionized, damaged molecules behind it. The most dangerous subset of galactic cosmic rays are what physicists call HZE particles. The H stands for high, the Z for atomic number, and the E for energy. These are the nuclei of heavy elements like iron and nickel, moving at significant fractions of the speed of light. When an HZE particle passes through biological tissue, it doesn't just bump into a few molecules. It obliterates everything along a narrow track, tearing apart DNA strands, destroying cell structures, and creating a column of radiation damage that the body struggles to repair. A single iron nucleus cosmic ray can damage thousands of cells along its path through the human body. On Earth, these particles are almost entirely blocked by the atmosphere. In interstellar space, they hit you directly. The unshielded radiation dose in interstellar space from galactic cosmic rays is estimated at roughly 400 to 600 millisieverts per year. Compare that to the 0.3 millisieverts per year you receive at sea level on Earth. You're talking about a dose rate roughly 1,000 to 2,000 times higher than what you experience on the ground. Over the course of a single year in unshielded interstellar space, you would receive a dose that significantly increases your lifetime cancer risk. Over a decade, the cumulative dose would be severe. Over a century, without shielding, the entire crew of a generation ship would be bathed in levels of radiation that would produce widespread cancer, cataracts, cardiovascular disease, neurological damage, and potentially heritable genetic mutations that would affect every subsequent generation born on the ship. So you need shielding. The question is what kind and how much. This is where the physics becomes deeply unforgiving. The most straightforward shielding approach is simply mass. Put enough material between the crew and the radiation, and you stop the particles. Water is excellent for this because hydrogen nuclei are close in mass to the incoming protons, so they absorb energy efficiently through collisions. Polyethylene, which is rich in hydrogen, is even better per unit mass. In theory, you could line the hull of the ship with a thick layer of water or polyethylene, several meters deep, and significantly reduce the radiation dose inside. Studies suggest that roughly 5 to 10 meters of water equivalent shielding would reduce the galactic cosmic ray dose by perhaps 50 to 70%. That's meaningful. It would bring the interior dose down from 400 to 600 millisieverts per year to perhaps 120 to 300 millisieverts per year. Better, but still far above what's considered safe for a general population living their entire lives in the environment. The recommended annual dose limit for radiation workers on Earth is 20 millisieverts per year. For the general public, it's 1 millisievert per year. Even with 5 to 10 meters of water shielding, the crew of a generation ship would be receiving doses 5 to 15 times higher than what's permitted for radiation workers on Earth. And they'd be receiving those doses continuously every year for their entire lives. And there's a complication. When high-energy galactic cosmic rays hit shielding material, they don't just stop. They interact with the nuclei of the shielding material and produce secondary particles, neutrons, pions, gamma rays, and fragments of shattered nuclei. These secondary particles can actually be more biologically damaging than the original cosmic ray in some cases. This is called the secondary particle cascade, and it means that adding more shielding doesn't always make things better in a simple, linear way. At a certain thickness, you've stopped most of the primary particles, but you've created a shower of secondary particles that partially offsets the benefit. There's an optimal shielding thickness beyond which adding more material produces diminishing returns. With current materials, that optimal point still leaves the crew exposed to a significant dose. What about magnetic shielding? In theory, you could create an artificial magnetic field around the ship, similar to Earth's magnetosphere, to deflect charged particles before they reach the hull. This approach has been studied extensively. The problem is scale. Earth's magnetic field works because it extends for tens of thousands of kilometers, giving charged particles a long distance over which to be gradually deflected. To create an equivalent deflection zone around a ship that's perhaps a few hundred meters across, you'd need a magnetic field of extraordinary intensity, and the energy required to sustain it would be enormous. Superconducting magnets could theoretically produce strong enough fields, but the engineering challenges are formidable. The magnets would need to be massive, cryogenically cooled for the entire voyage, and maintained without failure for centuries. A single quench event, where a superconducting magnet suddenly loses its superconductivity and dumps its stored energy as heat, could be catastrophic. And even a perfect magnetic shield wouldn't stop neutral particles, like the secondary neutrons produced by cosmic ray interactions, or gamma rays. As of now, no magnetic shielding system has been demonstrated at a scale or reliability level that would be practical for a generation ship. It remains a theoretical possibility, not an engineering solution. The honest assessment is this: With any shielding technology grounded in current physics, a generation ship crew would live their entire lives in a radiation environment significantly more intense than anything on Earth's surface. The dose could be reduced substantially, but probably not to Earth normal levels. The crew would experience elevated cancer rates. They would experience elevated rates of cataracts and cardiovascular disease. Most concerning, they would experience elevated rates of DNA damage in their reproductive cells, which means mutations that are passed to the next generation. Over many generations, this accumulated genetic damage could compound, interacting with the population genetics issues we'll discuss later. The radiation environment of interstellar space is not a solvable problem in the way that, say, propulsion is a solvable problem. It's a persistent, chronic threat that can be mitigated but probably not eliminated, and its effects accumulate silently across decades and centuries until they manifest as disease, reduced fertility, and generational decline. But radiation is patient. It does its damage quietly over years and decades. There's another form of decay that's just as patient, just as relentless, and in some ways even harder to combat. Mechanical decay. Everything breaks. This is not a philosophical statement. It's a law of nature. The second law of thermodynamics tells us that entropy, the tendency of ordered systems to become disordered, always increases in a closed system. Every material known to science degrades over time. Metals fatigue, developing microscopic cracks from repeated stress cycles that grow slowly until the part fractures. Seals made of rubber or polymer dry out, harden, lose their elasticity, and eventually fail to hold pressure. Bearings wear as surfaces rub against each other, even with lubrication, producing microscopic particles of debris that contaminate other systems. Electronic components degrade as electrons slowly migrate through semiconductor junctions. As solder joints develop whiskers, as insulating materials break down. Corrosion attacks metal surfaces wherever moisture and reactive chemicals are present. Adhesives lose their grip. Coatings peel. Wiring insulation becomes brittle. Optical surfaces cloud. Filters clog. Pumps lose efficiency. On Earth, none of this is a crisis. If a pump fails, you buy a new one. If a seal degrades, you replace it. If a circuit board fails, you swap it out. The global manufacturing infrastructure produces replacement parts for everything. The supply chain that supports modern civilization is vast, interconnected, and constantly replenishing itself. Even in Earth orbit, on the International Space Station, mechanical degradation is manageable because resupply missions bring replacement parts, new equipment, and raw materials. When the station's water recycling system develops a fault, NASA can send a replacement unit on the next cargo mission. When a cooling loop develops a leak, astronauts can install new hardware that was manufactured on Earth and launched specifically for this purpose. The International Space Station has been continuously occupied for over 25 years. And in that time, it has required constant maintenance and repair, with thousands of replacement parts delivered from Earth. Without those deliveries, the station would have become uninhabitable long ago. A generation ship cannot receive deliveries. Once it leaves the solar system, it is entirely on its own. Every replacement part, every spare component, every raw material needed for repairs must either be carried on board from the start, or manufactured on the ship during the voyage. Let's think about what that means practically. A large generation ship, one capable of supporting several thousand people for centuries, would be an enormously complex engineering system. It would contain life support systems with pumps, filters, fans, scrubbers, chemical processors, bioreactors, lighting arrays, irrigation networks, and atmospheric monitoring equipment. It would have power generation systems, likely nuclear reactors with turbines, generators, heat exchangers, coolant loops, control systems, and shielding. It would have structural components, the hull, bulkheads, pressure doors, airlocks, and the rotating sections that might be needed to provide artificial gravity. It would have water systems, food production systems, waste processing systems, communication systems, navigation systems, computing systems, and medical facilities. The total number of individual components in such a ship would easily be in the millions, possibly tens of millions. Each of these components has a finite lifespan. Some are robust and long-lived. Structural steel, for instance, can last for centuries if protected from corrosion. But most active components, the things that move, that carry current, that contain fluids, that experience thermal cycling, have lifespans measured in years or decades, not centuries. A high-quality industrial pump might last 20 to 30 years with proper maintenance. A circuit board might last 15 to 25 years before components drift out of specification. Seals and gaskets might last 5 to 15 years, depending on the material and conditions. Bearings, even high-quality ones, wear out, filters clog and must be replaced. Wiring insulation degrades. Now here's where reliability engineering becomes terrifying at interstellar timescales. Even if every individual component on the ship has a 99% chance of surviving any given year, when you have millions of components, failures happen constantly. With 1 million components each having a 99% annual survival rate, you'd expect roughly 10,000 component failures per year. That's about 27 failures per day, every single day, for centuries. The maintenance crew must identify, diagnose, and repair 27 failures per day just to keep up. And each repair requires spare parts, tools, skills, and time. If the repair rate falls below the failure rate, even slightly, a backlog develops. Unrepairable systems begin to accumulate. Redundant systems are called into service, but those redundant systems are also aging and degrading. Eventually, the backlog overwhelms the crew's ability to keep up, and systems begin to fail permanently. This is what engineers call the maintenance ceiling. It's the maximum rate at which a given crew, with given resources and skills, can perform repairs. If the failure rate exceeds the maintenance ceiling, the ship enters a decline spiral. More systems fail, which puts more stress on remaining systems, which accelerates their degradation, which produces more failures. Once this spiral begins, it is extremely difficult to reverse. On Earth, you escape this spiral by importing resources from outside. You bring in new equipment, hire more workers, access better technology. A generation ship has no outside. The maintenance ceiling is fixed by the ship's onboard resources, the crew's training, and the manufacturing capability carried on the vessel. And every year that passes, the problem gets slightly worse as the ship's stored resources are consumed and its material reserves diminish. This leads to a critical design question. Can the ship manufacture replacement parts during the voyage? In theory, yes. You could equip the ship with machine shops, three-dimensional printers, foundries, and fabrication equipment capable of producing many of the components the ship needs. Some generation ship proposals include extensive onboard manufacturing, essentially a small industrial base capable of producing everything from electronic circuits to structural members. But onboard manufacturing has its own problems. The manufacturing equipment itself degrades. A lathe wears out. A three-dimensional printer's components fail. A furnace lining erodes. You need the ability to manufacture not just spare parts for the ship, but spare parts for the machines that make spare parts. This is a recursive problem. Eventually, you need machines to make the machines that make the machines. And at each level, complexity accumulates, more skills are needed, more raw materials are consumed, and more things can go wrong. Raw materials are another constraint. You can carry a stockpile of metals, polymers, ceramics, and other materials at the start of the voyage, but that stockpile is finite. As you consume it making repairs and replacements, it diminishes, and you can't replenish it because there's nothing in interstellar space to mine. You might recycle materials from failed components, melting down broken parts to recast them, but recycling is never perfectly efficient. Some material is lost in every cycle. Alloys degrade in quality when repeatedly recycled. Over centuries, the material stock gradually deteriorates in both quantity and quality. There's also the problem of knowledge. Manufacturing and repair require skilled people. Not just people who can follow instructions, but people who understand the underlying engineering principles well enough to diagnose novel problems and improvise solutions. On Earth, this knowledge is distributed across millions of engineers, technicians, and scientists, supported by libraries, universities, and the accumulated experience of centuries of industrial civilization. On a generation ship, this knowledge must be maintained within a small community of perhaps a few thousand people across dozens of generations, without access to the broader intellectual infrastructure of Earth. Skills can be lost surprisingly quickly. Consider how much specialized industrial knowledge has been lost in communities that became isolated even on Earth. Techniques that were common a few generations ago become forgotten when the people who practice them die without passing on their knowledge. A generation ship must somehow ensure that every critical skill, every maintenance procedure, every diagnostic technique, every manufacturing process is transmitted accurately from one generation to the next, for centuries. If a generation fails to train enough qualified engineers, the maintenance ceiling drops, repairs slow, the failure backlog grows. Systems that could have been saved are instead lost permanently, and each lost system makes the next failure harder to absorb. The degradation of the ship's physical structure follows the same pattern. The hull, the rotating sections, the pressure bulkheads, all of these are under constant stress. If the ship uses rotation to produce artificial gravity, the structural members experience continuous centripetal loading. Over decades, even high-quality steel develops fatigue. Microscopic cracks form at stress concentration points, at weld joints, at bolt holes, at places where the geometry creates localized stress. These cracks grow slowly, sometimes imperceptibly, measured in fractions of a millimeter per year. But over a century, a crack that grows at 1/10 of a millimeter per year has advanced by 10 millimeters. Over 5 centuries, it's 50 millimeters. That's enough to compromise structural integrity. On Earth, we deal with fatigue in long-lived structures through regular inspection and replacement. Bridges are inspected for cracks. Aircraft are retired after a certain number of flight cycles. Pressure vessels in power plants are examined and replaced on a schedule. All of this depends on the availability of replacement parts and the ability to take the structure out of service for repair. A generation ship cannot take its hull out of service. It cannot replace its primary structural members. The ship's structure is fixed at construction. Whatever was built at the start is what must last for the entire voyage. If a primary structural element develops a critical fatigue crack 500 years into the mission, the crew must somehow repair it in place, under load, without the ability to fabricate a replacement of equivalent quality, using tools and materials that may have themselves degraded over 5 centuries of storage and use. The thermal environment adds another dimension to the problem. The ship's exterior faces the cold of interstellar space, roughly 2.7 degrees above absolute zero, while the interior must be maintained at habitable temperatures. This creates a constant thermal gradient across the hull. Thermal cycling as systems power up and down as areas of the ship transition between active use and dormancy creates expansion and contraction that stresses joints and seals. Over centuries, this thermal fatigue accumulates alongside the mechanical fatigue, compounding the structural degradation. Electronics face their own timeline of decay. Modern electronics are incredibly powerful, but not designed for century-scale lifetimes. Semiconductor devices degrade through mechanisms like electromigration, where metal atoms in circuit traces are gradually displaced by the flow of current, eventually causing open circuits or short circuits. Radiation accelerates this process. Galactic cosmic rays passing through electronic circuits can cause single event upsets, where a particle flips a bit in memory, or single event latch-ups, where a particle triggers a parasitic circuit that can damage or destroy a chip. Over time, cumulative radiation damage degrades the performance of transistors, increasing leakage current and reducing switching speed. The ship's computing and control systems would need to be radiation hardened, but radiation hardening reduces performance and increases size and power consumption. And even radiation hardened electronics have finite lifetimes. The ship would need the ability to manufacture replacement circuit boards, processors, and sensors, which requires maintaining a semiconductor fabrication capability on board. Even a modest chip fabrication facility is one of the most complex manufacturing systems humans have ever built. Maintaining one in a sealed ship for centuries is a challenge that borders on the absurd. The cumulative effect of all this degradation, structural, mechanical, electronic, material, is that the ship slowly becomes less capable over time. Every year, it's a little less reliable than the year before. The margins shrink, the redundancy erodes. Systems that once had triple backups now have double, then single, then none. This doesn't happen dramatically. There's no single moment of failure, no alarm that says the ship is dying. It happens gradually, like aging. A slow erosion of capability that accumulates imperceptibly until one day a critical system fails and there's no backup left. And here's what makes this so important for the survival question. The life support system, the ecosystem we discussed earlier, depends entirely on engineering systems. The plants need light, and that light comes from artificial lighting powered by the ship's reactor and electrical grid. The water cycle depends on pumps, filters, and treatment systems. The atmosphere depends on fans, scrubbers, and monitoring equipment. The food production depends on irrigation systems, nutrient delivery systems, and environmental controls. Every biological system on the ship is sustained by engineering systems. If the engineering systems degrade beyond a certain point, the biological systems collapse with them. The lights dim and the plants produce less oxygen. The pumps slow and the water cycle falters. The air scrubbers fail, and carbon dioxide builds up. The generation ship's survival is not determined by any single system. It's determined by the interaction of all systems together: biological and mechanical, ecological and structural, human and material. And all of them are degrading simultaneously, each one on its own timeline, but all of them trending in the same direction: toward failure. The question is not whether the ship will eventually fail. The question is when. And the answer depends on how well the ship was designed, how large its margins were at the start, how effectively the crew maintains it, and how much they can adapt as systems degrade. Optimistic estimates suggest that a very well-designed ship with extensive redundancy, robust manufacturing capability, and a highly trained crew might maintain viable operations for several centuries. Pessimistic estimates suggest that the accumulation of mechanical degradation, radiation damage, and material depletion could push a ship past its maintenance ceiling within 2 to 3 centuries, initiating a decline spiral that would be very difficult to reverse. The honest answer is that we don't know. We've never built anything that needed to function for this long without external support. The longest functioning human artifacts, cathedrals, aqueducts, some bridges, have lasted centuries, but they required continuous maintenance and repair using materials sourced from the surrounding environment. A generation ship has no surrounding environment. It has only itself. And what it has must last as long as the journey lasts, or the journey ends. But even if the engineering holds, even if the ecosystem remains stable, even if the radiation is manageable, there is another clock ticking inside every person on the ship. A biological clock that has nothing to do with machines or plants or cosmic rays. It has to do with the fundamental nature of human genetics and what happens to a small, isolated population over many generations. And that clock, as it turns out, may be the hardest one of all to stop. Every person alive today carries roughly 20,000 to 25,000 genes. These genes are organized across 23 pairs of chromosomes, and together they form a blueprint that governs everything from the color of your eyes to the efficiency of your immune system, the density of your bones, the way your body processes food, the speed at which your neurons fire, and your susceptibility to hundreds of different diseases. But here's the thing that matters for a generation ship. You don't just carry one copy of each gene. You carry 2, one inherited from your mother and one from your father. And across the human population, most genes exist in multiple versions called alleles. Some alleles are common, some are rare, some are beneficial, some are neutral, and some are harmful, capable of causing disease or reducing fitness if the wrong combination comes together in a single individual. In a large population, harmful alleles are kept in check by a simple mechanism. They're rare. If a harmful allele exists in 1 out of every 1,000 people, but the chances of 2 carriers meeting, reproducing, and producing a child who inherits 2 copies of that harmful allele are very low. 1 in 1,000 times 1 in 1,000 is 1 in a million. In a population of millions or billions, some unlucky individuals will draw that short straw, but the vast majority won't. The harmful allele persists at low frequency, causing occasional problems but never threatening the population as a whole. Now, shrink that population. Put 5,000 people on a generation ship and seal the door. Those 5,000 people carry a sample of the human gene pool, but only a sample. They don't carry every allele that exists in the human species. Rare alleles may be missing entirely. Others may be present at higher frequencies than in the general population simply by chance, depending on which 5,000 individuals were selected. This is called the founder effect, and it's the first genetic problem a generation ship faces before the voyage even begins. The founder effect has been documented repeatedly in human history. When a small group splits off from a larger population and becomes isolated, the new group carries only a fraction of the original genetic diversity. The Amish communities in the United States descended from a few hundred German-speaking immigrants in the 18th century. Because of their small founding population and their tradition of marrying within the community, certain genetic disorders are far more common among the Amish than in the general population. Ellis Van Creveld syndrome, a rare disorder causing short stature and extra fingers, occurs in the Amish at rates roughly 100 times higher than in the broader population. This isn't because the Amish did anything wrong, it's because their founding population happened to carry those alleles at slightly higher frequencies, and centuries of limited genetic mixing concentrated them. The Ashkenazi Jewish population shows a similar pattern. Centuries of relative genetic isolation within European societies led to elevated frequencies of certain disease alleles. Tay-Sachs disease, Gaucher disease, and several other genetic disorders are significantly more common in Ashkenazi populations than in the general human population. Again, this isn't a flaw in the population, it's a mathematical consequence of small founding size and limited gene flow from outside. A generation ship population would face the same dynamics, but more extreme. The founding population is chosen once, the door closes, and from that moment forward, every child born on the ship draws its genetic material exclusively from the existing shipboard gene pool. No new genetic material enters the system. Ever. For the entire duration of the voyage. The gene pool can only shrink, it cannot grow. This is where the concept of minimum viable population becomes critical. Population geneticists have studied extensively how small a population can be and still remain genetically healthy over long periods. The answer depends on what you mean by healthy and how long you mean by long, but the numbers that emerge from modeling and from real-world observations are sobering. A commonly cited benchmark is what geneticists call the 5,500 rule. 50 individuals is roughly the minimum needed to avoid severe inbreeding depression in the short term, over a few generations. 500 individuals is roughly the minimum needed to maintain enough genetic diversity to adapt to changing conditions over the medium term, over dozens of generations. But these numbers were developed for wildlife conservation. For populations that might experience occasional gene flow from neighboring populations and that exist in a natural environment with natural selective pressures. A generation ship population has no gene flow. Zero. And it exists in a radically artificial environment where selective pressures are completely different from anything human genetics evolved under. More recent modeling specifically targeting generation ship scenarios has produced larger numbers. A study published in 2014 by anthropologist Cameron Smith at Portland State University estimated that a generation ship would need a minimum founding population of roughly 10,000 individuals, with approximately 40,000 being a safer target. Smith's model accounted for catastrophic events, disease outbreaks, accidents, and other population shocks that could suddenly reduce the population below recovery thresholds. With only a few thousand people, a single epidemic or a single major system failure that kills a significant fraction of the crew could push the population below the point of genetic viability. With 10,000 or more, the population has a buffer against these shocks. Other researchers have produced different numbers depending on their assumptions, but the general consensus is that you need at least several thousand individuals, and preferably more, to maintain a genetically healthy population over centuries. Below about 500, the math becomes very grim very quickly. Below about 100, it becomes essentially impossible without aggressive technological intervention in reproduction. Let me explain why. Because the mechanisms matter, the first and most intuitive problem is inbreeding. In a small, closed population, eventually everyone becomes related to everyone else. This is mathematically inevitable. If you start with 5,000 people and they reproduce at normal human rates, within roughly 10 to 15 generations, depending on mating patterns, every individual in the population will share common ancestors. They'll all be at least distant cousins. And as generations pass, the degree of relatedness increases. Inbreeding, the mating of related individuals, increases the probability that offspring inherit two identical copies of the same allele, one from each parent, both ultimately descended from the same ancestor. This is called homozygosity. Some increase in homozygosity is harmless, but many harmful alleles are recessive, meaning they only cause problems when an individual has two copies. A single copy is masked by a functional allele on the other chromosome. The individual is a carrier but is otherwise healthy. When two carriers produce a child, there's a 1 in 4 chance the child inherits two copies of the harmful allele and develops the disease. In a large population, the chance of two carriers meeting is low because the harmful allele is rare. In a small, closed population where everyone is related, the chance increases dramatically. Both parents may have inherited the same harmful allele from the same distant ancestor. The allele isn't rare within this population anymore. It may be present in a significant fraction of individuals. The result is called inbreeding depression, a measurable decline in population fitness caused by the increased expression of harmful recessive alleles. Inbreeding depression manifests as reduced fertility, higher infant mortality, weaker immune systems, greater susceptibility to disease, lower birth weight, slower growth, and shorter lifespan. It has been documented extensively in animal populations. Island populations of mammals, small zoo populations, and isolated human communities all show measurable effects. The severity depends on the degree of inbreeding, but even modest inbreeding levels produce detectable effects. And on a generation ship, the inbreeding level rises with every generation because there's no way to introduce new genetic material. The second mechanism is genetic drift. In a large population, allele frequencies remain relatively stable from one generation to the next, because the large number of individuals ensures that statistical averages hold. But in a small population, random chance plays a much larger role. Some individuals reproduce more than others. Some die before reproducing. Some alleles are passed on more frequently than expected, while others are passed on less frequently, purely by luck. Over time, this randomness causes allele frequencies to wander unpredictably. Some alleles drift to higher and higher frequencies until they become fixed, present in every individual. Others drift to lower and lower frequencies until they disappear entirely. This process is random with respect to whether the allele is beneficial, neutral, or harmful. A beneficial allele can be lost through drift just as easily as a harmful one can become fixed. The smaller the population, the stronger the effect of drift, and the faster genetic diversity is lost. This matters enormously for a generation ship, because genetic diversity is the raw material of adaptation. If the population encounters a new pathogen, a disease that evolves aboard the ship or is introduced from stored biological samples, or from the ship's own microbial ecosystem, the population's ability to survive that pathogen depends on having a diversity of immune system genes. If genetic drift has eroded that diversity, the entire population may be vulnerable. The same pathogen could sweep through the ship and kill or incapacitate a large fraction of the crew because their immune systems all share the same weaknesses. The human immune system is governed in part by a set of genes called the major histocompatibility complex, or NTSLMHC, also known as the human leukocyte antigen system, or HLA. These genes are among the most variable in the entire human genome. In a large human population, there are thousands of different HLA alleles. This diversity is what allows the human species as a whole to fight off a vast array of different pathogens. Different people have different HLA types, which means different people are resistant to different diseases. No single epidemic can wipe out everyone because there's always a fraction of the population whose immune system happens to be well suited to fighting that particular pathogen. In a small, closed population, HLA diversity erodes through drift. Over many generations, alleles are lost. The population's immune repertoire narrows, and the risk of a catastrophic epidemic, one that the population lacks the genetic tools to fight, increases with every generation. There is a concept in population genetics called the effective population size, abbreviated as NE. This is not the same as the actual census population. The effective population size is the number of individuals who are actually contributing genes to the next generation. It's always smaller than the census count, often much smaller. Not everyone reproduces. Some people have many children, others have none. Age structure matters. Sex ratios matter. If the population has unequal numbers of males and females, the effective population size drops. If some individuals are excluded from reproduction for social, medical, or practical reasons, the effective population size drops further. In a generation ship population of 5,000, the effective population size might be only 2,000 to 3,000, depending on social structure and reproductive patterns. And it's the effective population size, not the census number, that determines the rate of genetic drift and inbreeding. This means that even a ship carrying 5,000 people might experience genetic erosion at a rate equivalent to a much smaller population. Over centuries, the cumulative effect is a steady, irreversible loss of genetic diversity. Each generation is slightly less diverse than the one before. Harmful alleles become slightly more common. Immune diversity narrows slightly. Fertility drops slightly. Disease susceptibility increases slightly. No single generation notices the change because it's gradual, but over 10, 20, 30 generations, the decline compounds. The population becomes measurably less healthy, less fertile, less resilient, and at some point it crosses a threshold below which recovery is no longer possible without outside genetic input. That input doesn't exist on a generation ship. Could technology solve this? In theory, several interventions are possible. Genetic screening of embryos could identify and prevent the most harmful combinations of alleles. Assisted reproduction technologies could ensure that mating patterns are optimized for genetic diversity rather than left to individual choice. Stored genetic material, frozen sperm and egg cells, or even stored DNA sequences could be used to artificially introduce diversity into the population, essentially creating new individuals from genetic material collected before the voyage. These are real possibilities, and most serious generation ship proposals include some form of genetic management, but each comes with serious complications. Genetic screening requires advanced medical technology that must be maintained for the entire voyage. If the screening equipment fails and can't be repaired, the intervention stops. Managed reproduction requires that individuals accept external control over their reproductive choices, something that raises profound ethical questions and has historically provoked intense resistance in human societies. And stored genetic material has its own lifespan. Frozen biological samples degrade over time, even in ideal conditions. Cosmic radiation damages stored DNA. Over centuries, the viability of stored samples declines. How long can frozen embryos or sperm cells remain usable? Decades, probably. A century, possibly. 5 centuries? That pushes well beyond anything we've tested. There's also the question of what happens to human biology in the ship's artificial environment, even apart from genetics. Human beings evolved over millions of years in Earth's specific gravitational, atmospheric, and radiation environment. A generation ship would provide a different environment, almost certainly different in gravity, radiation exposure, atmospheric composition, microbial ecology, and sensory experience. If the ship uses rotation to simulate gravity, the gravity experienced by the crew depends on where they are relative to the axis of rotation. Near the outer rim, gravity might approximate Earth's. Near the axis, it could be significantly lower. People living and working in different parts of the ship might experience different gravitational environments. The human body responds to gravity in profound ways. Bone density, muscle mass, cardiovascular function, fluid distribution, and even the development of the vestibular system in the inner ear are all shaped by the gravitational environment. We know from studies aboard the International Space Station that prolonged exposure to microgravity causes bone loss, muscle atrophy, cardiovascular deconditioning, vision problems from increased intracranial pressure, and immune system changes. These effects are partially reversible when astronauts return to Earth's gravity. But on a generation ship, the crew never returns to Earth's gravity. If the simulated gravity is slightly lower than Earth's, perhaps 80 or 90% of Earth normal, the long-term effects across generations are unknown. Would human bodies gradually adapt to the lower gravity across generations? Would bone density decline to a new equilibrium? Would muscle development change? Would the cardiovascular system restructure? We don't know. No one has ever studied multi-generational human development in non-Earth gravity because we've never had anyone live their entire life, let alone raise children, in any gravitational environment other than Earth's 1G field. Reproduction itself might be affected. Mammalian reproduction is a remarkably complex process that evolved under Earth gravity. Fertilization, implantation, embryonic development, fetal growth, and birth all occur in a 1G environment with specific fluid dynamics, cellular signaling, and mechanical forces. Some studies in rodents exposed to altered gravity conditions have shown changes in reproductive outcomes, including altered embryonic development and reduced fertility, though the results are mixed and the research is limited. We simply don't know whether human beings can reproduce successfully in reduced gravity over multiple generations. If fertility declines even slightly in the ship's environment, say by 5 or 10% per generation, the effect compounds across centuries. A small reduction in fertility in Generation 1 becomes a significant population decline by Generation 10. The radiation environment compounds these concerns. As we discussed, the crew would be exposed to elevated radiation levels even with shielding. Radiation damages DNA, and while the body has repair mechanisms, those mechanisms aren't perfect. Some damage is repaired incorrectly, introducing mutations. Most mutations are neutral or harmful. Beneficial mutations are exceedingly rare. In reproductive cells, mutations are passed to the next generation. Over many generations, the mutation load, the total burden of slightly harmful mutations carried by the population, increases. In a large population on Earth, natural selection efficiently removes the most harmful mutations. Individuals carrying heavy mutation loads are less likely to survive and reproduce, so those mutations are weeded out. But natural selection is less efficient in small populations because genetic drift can override it. A slightly harmful mutation that would be eliminated by selection in a large population might drift to high frequency in a small one simply by random chance. Over centuries, the mutation load in a generation ship population could increase significantly, contributing to a gradual decline in average health, fertility, and cognitive function. This process is called mutational meltdown, and it has been observed in small laboratory populations of organisms. When a population is small enough and isolated enough, the accumulation of harmful mutations eventually overwhelms the population's ability to compensate, leading to a terminal decline in fitness and eventual extinction. The threshold depends on population size, mutation rate, and the severity of the mutations, but it is a real and documented phenomenon. For a generation ship, the mutation rate is higher than on Earth because of the elevated radiation exposure. The population is small by any genetic standard, and the population is completely isolated with zero gene flow. All three conditions that accelerate mutational meltdown are present simultaneously. This doesn't mean meltdown is inevitable, but it means the risk is real and increases with every generation that passes. The biological clock of a generation ship, then, is not a single mechanism, but a convergence of several. Inbreeding depression reduces fitness and fertility. Genetic drift erodes diversity, particularly immune diversity. Mutational accumulation increases the burden of harmful alleles. Environmental factors, altered gravity, elevated radiation, and artificial ecosystems introduce additional pressures on reproduction and development that are largely unstudied. Each of these processes operates independently, but they all push in the same direction, toward declining population health over time. The timeline depends on the starting population size. With a founding population of 500, genetic modeling suggests that inbreeding depression would become severe within roughly 6 to 10 generations, perhaps 150 to 300 years. With 5,000, the timeline extends perhaps to 20 or more generations, 500 years or longer. With 10,000 or more, the population might sustain genetic viability for 1,000 years or more, assuming effective genetic management practices are maintained. But these estimates assume that everything else goes right, that the ship's life support system keeps working, that the medical technology keeps functioning, that the social systems that govern reproduction remain intact, that no catastrophic events, epidemics, accidents, or conflicts suddenly reduce the population below critical thresholds. In reality, the biological clock doesn't tick in isolation. It ticks alongside the engineering clock, the ecological clock, and one more clock that may be the most unpredictable of all. Because a generation ship isn't just a machine carrying a population. It's a civilization. A society sealed inside a metal container for centuries, with no exit, no immigration, no contact with the larger human world, and no shared experience beyond the walls of the ship. And civilizations, as we know from the entirety of human history, are fragile things. They rise and they fall, they fracture from within, they lose their way, they forget why they started. And on a generation ship, a civilization that fails doesn't just collapse into a dark age from which it might eventually recover. It collapses into extinction. Because there is nowhere else to go, nothing else to fall back on, and no one coming to help. That's the final layer of the problem. And in many ways, it may be the one that determines everything. Everything we've discussed so far, the closed-loop ecosystem, the radiation, the mechanical decay, the genetics, all of it assumes that the people on the ship cooperate, that they work together, that they maintain the systems, follow the protocols, train the next generation, manage reproduction responsibly, and keep the mission going across centuries. That's an enormous assumption, because human beings, for all our brilliance and adaptability, have never once in the entire history of our species maintained a single stable social order for more than a few centuries. And most have lasted far less. Think about what a generation ship actually is from a social perspective. It's a small community of several thousand people locked inside a container with no way out. They can't leave. They can't emigrate. They can't go somewhere else if they don't like how things are being run. They can't trade with outsiders. They can't receive new ideas, new technologies, new cultural influences, or new people from the outside world. They are sealed off from the rest of humanity completely and permanently. And they must remain functional as a society, not for a decade, not for a lifetime, but for centuries. For 10, 20, or 30 generations. Generations of people who didn't choose this mission, who were born into it, who have never seen Earth, who have never breathed unrecycled air or walked under an open sky, and who may have no emotional connection to either the origin or the destination. The first generation, the founders, chose to be there. They understood the mission. They trained for it. They believed in it strongly enough to leave behind everything they knew. They had purpose, motivation, and a direct personal connection to the goal. They remembered Earth. They could tell stories about forests, oceans, wind, and rain. They carried the emotional weight of the sacrifice they made, and that weight gave meaning to the hardship. But the second generation didn't choose. They were born on the ship. Earth is something their parents talk about, a story, a collection of images and recordings, not a lived experience. The destination star is an abstraction, a point of light their grandchildren's grandchildren might see. The mission is something they inherited, not something they chose. Their entire world is the ship. The corridors, the agricultural bays, the recycling systems, the hum of the reactors. This is their normal. And for the second generation, the mission may still hold meaning because their parents can communicate the passion and purpose directly. By the fifth generation, Earth is ancient history. Nobody alive has ever met anyone who walked on Earth. The stories have been passed down and retold so many times that they've become mythology rather than memory. The destination star is still centuries away. It's not a goal you're working toward. It's a concept so distant it might as well be imaginary. Your entire life will be spent on this ship. Your children's entire lives will be spent on this ship. What exactly are you working toward? Why are you maintaining the water recycling system at 3 in the morning when the alarm goes off? Why are you studying reactor engineering when you could be doing something more immediately rewarding? Why should you accept restrictions on who you can reproduce with when those restrictions are based on genetic calculations you don't fully understand and don't emotionally connect with? This is the problem of purpose erosion, and it is one of the most dangerous threats a generation ship faces. Because every system on the ship, every piece of technology, every ecological loop, every genetic management protocol depends on people actively maintaining it. If the crew loses motivation, if they stop caring about the mission or stop believing it matters, maintenance lapses. Training becomes less rigorous, protocols are relaxed, shortcuts are taken, and the ship begins to decay faster than it otherwise would. Not because of physics or biology, but because of psychology. We have some historical analogues that offer glimpses of what happens to isolated human communities over extended periods, and the patterns are not reassuring. Pitcairn Island is one of the most striking examples. In 1790, the mutineers from HMS Bounty, along with a group of Tahitian men and women, settled on Pitcairn, a remote and virtually inaccessible island in the South Pacific. It was one of the most isolated communities in human history. Within the first few years, violence erupted. Of the 15 men who arrived on the island, 11 were dead within 4 years, most murdered by each other in disputes over resources and women. Within a decade, only 1 man remained alive. The surviving community eventually stabilized, but only after nearly destroying itself. And this was a group of people on an island with fresh water, arable land, breathable air, and sunlight. They had resources that a generation ship crew could only dream of. Yet isolation, confinement, and the absence of external social structures nearly wiped them out within a single generation. The Antarctic research stations provide another data point. These stations house small crews in isolated, confined environments for months at a time. The psychological effects are well documented. Crew members experience what researchers call the winter over syndrome, a cluster of symptoms including irritability, insomnia, cognitive impairment, depression, interpersonal hostility, and a tendency to form factions. Sleep patterns deteriorate, motivation drops, minor disagreements escalate into serious conflicts. And this is among carefully screened, highly trained professionals who know their tour of duty is temporary, who can communicate with the outside world, and who will return home within a year or two. Submarine crews show similar patterns. Nuclear submarines can remain submerged for months at a time, and the crews operate in confined, monotonous environments with rigid hierarchies and limited personal space. The psychological strain is significant. Anxiety, depression, and interpersonal conflict are common. The military mitigates these effects through strict discipline, careful crew selection, regular rotation, and the knowledge that the deployment is temporary. A generation ship crew has none of these mitigations. There is no rotation. There is no going home. The deployment is a permanent and involuntary for every generation after the first. Even Biosphere 2, which we discussed in the context of ecological failure, demonstrated severe social breakdown. The 8 crew members, who began the experiment as colleagues and in some cases friends, split into 2 hostile factions within the first year. Communication between the factions deteriorated to the point where some members refused to speak to others. The interpersonal conflict became so severe that it interfered with the crew's ability to manage the failing ecological systems. And again, these were volunteers who knew the experiment would end in 2 years, who could see the Arizona desert through the glass, and who could have walked out in an emergency. A generation ship multiplies every one of these stressors by orders of magnitude. The confinement is permanent, the monotony is unbroken, the environment is entirely artificial. There is no nature, no weather, no seasons in the traditional sense, no horizon, no open sky. The psychological effects of living in such an environment for an entire lifetime, from birth to death, are completely unknown. We can extrapolate from shorter duration analogues, but the extrapolation is necessarily speculative because no human community has ever lived under these conditions. Then there's the problem of governance. How do you run a civilization inside a ship for centuries? This is not a trivial question. It may be the most difficult political problem ever conceived. On Earth, governments rise and fall. Democracies can be voted out of power. Dictatorships can be overthrown. People can emigrate if they disagree with how their country is run. There are checks and balances, external pressures, international norms, and the raw possibility of revolution. On a generation ship, many of these corrective mechanisms don't exist or become extremely dangerous. Consider democracy. In theory, the ship could be governed democratically, with the crew voting on leadership and policies. But democracy requires an informed electorate, and maintaining an informed electorate across centuries of isolation is extraordinarily difficult. Democratic systems also tend to prioritize short-term preferences over long-term necessities. If the crew votes to relax the genetic management protocols because they find them oppressive, if they vote to reduce the maintenance schedule because they'd rather have more leisure time, if they vote to increase food rations now at the expense of reserves for the future, democratic decision-making could actively undermine the ship's long-term survival. The mission requires certain things regardless of whether the crew wants them. The air must be recycled. The reactor must be maintained. The genetic diversity must be managed. These are not optional. They are survival requirements. And any governance system must ensure they happen even if the current generation doesn't feel like doing them. Consider authoritarianism. A strong centralized authority could enforce maintenance schedules, genetic protocols, and resource allocation without needing popular approval. This might be more efficient at ensuring the ship's systems are maintained. But authoritarian systems have their own failure modes. They concentrate power, which invites corruption. They suppress dissent, which prevents the identification of problems. They depend on the quality of the leader, and producing competent leaders generation after generation through centuries of isolation is not something any authoritarian system has ever achieved. Dynastic succession produces incompetent leaders within a few generations, almost without exception. Meritocratic selection requires institutions that can reliably identify and promote talent, and those institutions are themselves vulnerable to corruption and decay. History offers no model of a government that has remained stable and functional for more than a few centuries. The Roman Republic lasted about 500 years before becoming the Roman Empire. The Byzantine Empire lasted about 1,000 years, but it went through dozens of crises, civil wars, and near collapses during that time. The Catholic Church has lasted 2,000 years as an institution, but it's been riven by schisms, corruption, and periods of near irrelevance. And all of these institutions existed in a world with external pressures, external resources, and external populations to draw upon. None of them operated in a sealed container with no outside contact. A generation ship's government must somehow remain legitimate, competent, and functional for longer than any government in human history has ever lasted, and it must do so under conditions that are far more challenging than anything any government has ever faced. If governance fails, if the political system collapses into factional conflict, or hardens into a tyranny that prioritizes its own power over the ship's needs, or simply becomes incompetent through generational decay, then maintenance lapses, resource allocation becomes irrational, and the ship's physical and biological systems begin to fail. There's also the problem of social stratification. In any small, closed community, hierarchies tend to form. Some people have more power, more resources, or more status than others. Over generations, these hierarchies can harden into rigid class systems. The families that control the ship's key systems, the reactor, the agricultural bays, the water recycling, might accumulate disproportionate power. A technical elite could emerge that controls the knowledge necessary to keep the ship running, and uses that knowledge as leverage to dominate the rest of the population. Or conversely, a political elite could emerge that controls governance and uses its authority to extract privileges from the technical class. Either way, the result is internal conflict that diverts energy and attention from the ship's actual survival needs. Resource conflicts are virtually guaranteed. On a ship with finite resources, every allocation decision is a zero-sum game. More food for one group means less for another. More space for agriculture means less living space. More energy for manufacturing means less for heating or lighting. These trade-offs must be made continuously, and they must be made fairly, or at least perceived as fair, to prevent resentment from building into open conflict. On Earth, resource conflicts can be resolved through trade, migration, or the discovery of new resources. On a generation ship, none of these options exist. Every conflict must be resolved internally, within a closed community that has no escape valve. Cultural drift is another long-term threat. Human cultures change over time. Languages evolve, values shift, traditions are reinterpreted or abandoned. On Earth, this is a natural and generally harmless process because cultures interact, exchange ideas, and adapt. But on a generation ship, cultural drift occurs in isolation. The crew's culture will inevitably change over centuries, but it will change without any external reference point, without the corrective influence of contact with other human societies. This drift could move in unpredictable directions. Consider the possibility that the ship's culture gradually loses its commitment to the mission itself. The mission, after all, was chosen by the founders. Later generations inherit it, but inheritance doesn't guarantee acceptance. What if, 10 generations in, the dominant culture on the ship decides that the mission was a mistake, that the destination is undesirable, that they'd rather redirect the ship or simply live permanently in space or abandon the maintenance-intensive systems in favor of a simpler way of life? What if a religious movement arises that reinterprets the mission, declaring the destination to be spiritually forbidden, or the ship itself to be a sacred space that must not be altered? These aren't absurd scenarios. They're exactly the kind of cultural transformations that happen in isolated communities across far shorter timescales. The history of isolated religious communities, utopian settlements, and colonial outposts is filled with examples of communities that radically reinterpreted their founding mission within a few generations. sometimes in ways that undermine their own survival. Perhaps the most haunting historical analogue is Rapa Nui, known in the West as Easter Island. A small Polynesian community colonized this remote island roughly 800 to 1,000 years ago. They developed a complex society, built monumental stone statues, and created a sophisticated culture. But the island's resources were finite. The forests were cleared for agriculture and for transporting the statues. Soil eroded, crop yields declined. The bird populations that provided protein were hunted to extinction. As resources dwindled, the social order collapsed. Warfare broke out between clans. The population crashed. By the time Europeans arrived in 1722, the once thriving civilization had largely destroyed itself. The parallels to a generation ship are uncomfortable. A small population on an isolated platform with finite resources, consuming those resources faster than they can be replenished, with no possibility of resupply from outside. Rapa Nui had far more natural resources than a generation ship would have. It had rainfall, sunlight, soil, and ocean, and is still collapsed. A generation ship has only what it carries, and every resource that is wasted or mismanaged is gone forever. Knowledge loss is a related and equally dangerous threat. The ship's survival depends on maintaining a vast body of technical knowledge across generations. Reactor physics, agricultural science, ecology, medicine, genetics, materials science, computer engineering, structural engineering, water chemistry, atmospheric science. Each of these fields must be taught, learned, and practiced by enough people in each generation to ensure continuity. If any critical field loses its practitioners, if a generation fails to produce enough trained engineers or doctors or agronomists, the ship loses a capability it may never recover. On Earth, knowledge is distributed across billions of people and stored in millions of books, databases, and institutions. Losing knowledge in one location doesn't matter because it exists elsewhere. On a generation ship, knowledge exists only in the minds of the crew and in whatever physical or digital archives the ship carries. If the archives degrade, if the digital storage systems fail, if the crew stops studying the archives because they've lost interest in the material, then knowledge disappears. And once it's gone, there may be no way to recreate it. So let's bring everything together and attempt an answer to the question we started with. How long could a generation ship really survive in deep space? The answer is not a single number. It's a set of overlapping timelines, each defined by a different failure mode. And the ship survives only as long as all of them hold simultaneously. The ecological timeline is perhaps the shortest. Maintaining a closed-loop biosphere that supports thousands of people is beyond our current capability. Our best attempt, Biosphere 2, failed within 2 years for 8 people. A generation ship would need to do vastly better, and it would need to do it for vastly longer. With significant advances in ecological engineering and robust monitoring systems, it might be possible to maintain a functional ecosystem for decades to a few centuries. But the smaller and more artificial the ecosystem, the more fragile it is, and the more likely that a cascading failure will overwhelm it. The ecological clock probably sets an upper limit measured in centuries, unless the ship is very large and the ecosystem very carefully designed with deep redundancy. The engineering timeline is somewhat longer, but equally relentless. Mechanical systems degrade, materials fatigue, electronics fail. Without external resupply, the ship must manufacture its own replacement parts using a finite stockpile of raw materials. The maintenance ceiling, the maximum rate at which repairs can be performed, is fixed by the crew's skills and the ship's manufacturing capability. If the failure rate exceeds the maintenance ceiling, the ship enters a decline spiral. Optimistic estimates place this threshold at several centuries for a well-designed ship with extensive redundancy. Pessimistic estimates place it at 2 to 3 centuries. The engineering clock likely allows survival for several hundred years, perhaps longer with very advanced manufacturing and very large initial margins. The genetic timeline is the slowest of the biological clocks, but also the most inexorable. With a founding population of several thousand, genetic modeling suggests that inbreeding depression and drift become serious problems after roughly 10 to 20 generations, which translates to roughly 300 to 600 years. With a larger founding population, 10,000 or more, and active genetic management, the timeline might extend to 1,000 years or beyond. But genetic management requires functioning medical technology, social cooperation, and institutional continuity, all of which are threatened by the other failure modes. And the social timeline is the most unpredictable. Human societies can collapse in a single generation if conditions are bad enough. They can also persist for centuries if conditions are favorable. A generation ship's social stability depends on governance, psychological well-being, cultural continuity, resource fairness, and the maintenance of purpose across generations that never chose the mission. History offers no example of a closed, isolated community maintaining social stability for more than a few centuries. And most examples of isolated communities show significant dysfunction within a few generations. But listing these timelines separately doesn't capture the real danger. Because these clocks don't tick independently. They're connected. And the connections between them are what make a generation ship so fundamentally precarious. Let me walk you through how this actually plays out. Imagine the ship is 300 years into its voyage. The founders are long gone. The current generation is the 10th or 11th to live aboard. The ship's ecosystem has been running for 3 centuries, and it's showing strain. The soil microbiome in the agricultural bays has been slowly losing diversity. Crop yields have been declining by a fraction of a percent per year for the last 50 years. Individually, these annual declines are barely noticeable, but compounded over 5 decades, total food production has dropped by roughly 15 to 20% from its peak. The crew has adjusted. Portions are smaller. Some luxury crops have been abandoned in favor of calorie-dense staples. The diet is monotonous. People are healthy enough, but not thriving. Morale is lower than it was a generation ago. At the same time, the ship's engineering systems have accumulated 3 centuries of wear. The reactor is on its second core. The replacement core was manufactured on board 60 years ago using materials that were themselves recycled from the original stockpile. It works, but its output is about 8% lower than the original. The lighting arrays in the agricultural bays have been replaced multiple times. But the most recent generation of replacement bulbs produces a slightly different spectrum. Because the phosphor compounds available for manufacturing have changed, as raw materials have been recycled through multiple generations of use. The plants are still growing, but photosynthetic efficiency is slightly reduced because the light spectrum isn't optimal. This compounds the soil problem. Yields drop a little further. The maintenance backlog has been growing for decades. Not dramatically, not in a way that triggers alarms, but the ratio of maintenance requests to completed repairs has been slowly shifting in the wrong direction. 15 years ago, the crew could address 95% of all maintenance requests within a week. Now it's 87%. The difference sounds small, but it means that 13% of failures are sitting unresolved for longer, and some of those unresolved failures cascade into other systems. A corroded pipe fitting that doesn't get replaced leaks slightly, and the leaked fluid causes humidity damage in an adjacent electronics bay, which degrades sensors that monitor atmospheric composition. The degraded sensors produce less accurate readings, which means the atmospheric management system responds more slowly to changes. Carbon dioxide spikes go unnoticed for slightly longer. The crew experiences more frequent headaches. Cognitive performance dips slightly across the population. Maintenance workers are a little less sharp. The repair rate drops a tiny bit more. Meanwhile, the genetic management program has been running for 10 generations, but it's under pressure. The medical equipment needed for embryo screening was damaged in an electrical fire 40 years ago. The crew repaired most of it, but one critical component, a specialized optical sensor, could not be replicated with onboard manufacturing. Without it, the screening process is less precise. Some harmful allele combinations that would previously have been identified are now slipping through. The population's genetic counselors know this, but they can't fix it. They've compensated by tightening the mating recommendations, asking more people to accept partners they wouldn't have chosen. This has created resentment. A faction in the ship's governing council has begun arguing that the genetic protocols are too intrusive, that they violate personal freedom. Several council members were elected partly on the promise of relaxing these restrictions. The councillors warn that relaxation will accelerate inbreeding depression. The council debates. The debate becomes acrimonious. Trust between the technical staff and the political leadership erodes. A charismatic figure emerges. Someone who argues that the mission itself was a mistake. That the original founders had no right to condemn their descendants to centuries of confinement. That the destination star, still over a century away, is a fantasy. That the crew should focus on making life aboard the ship as comfortable as possible, rather than sacrificing for a goal they'll never see. This argument resonates with a significant portion of the population, especially the younger generation. Support for the mission weakens. Training enrollment in engineering and agricultural science drops. Fewer young people want to spend their lives maintaining systems for a destination they don't believe in. The maintenance ceiling drops further. The failure backlog grows. Nothing in this scenario is dramatic. There is no single catastrophe, no explosion, no plague, no mutiny. There is only the slow, quiet accumulation of small failures, each one making the next one slightly more likely. The ecosystem degrades because the engineering degrades. The engineering degrades because the social systems that train and motivate maintenance workers are weakening. The social systems are weakening because the genetic management is becoming intrusive and the mission has lost its emotional hold. The genetic management is becoming intrusive because the medical equipment failed and couldn't be fully repaired. And the medical equipment failed because the engineering backlog allowed conditions to develop that led to an electrical fire. Every failure feeds the others. The web tightens, the margins shrink, and somewhere, years or decades down this trajectory, the system crosses a threshold from which recovery is no longer possible. Not because any single catastrophic event occurred, but because the cumulative weight of 1,000 small degradations finally exceeded the system's capacity to compensate. This is how a generation ship dies. Not with a bang, but with a slow fade. Given all of this, what can we say? For a small ship carrying a few hundred people with limited redundancy, survival beyond a few decades is uncertain, and survival beyond a century is unlikely. For a medium ship carrying several thousand people with good engineering and active genetic management, survival for 1 to 3 centuries is plausible but not guaranteed, and survival beyond 5 centuries is optimistic. For a very large ship carrying 10,000 or more people with extensive redundancy, advanced manufacturing, robust ecological systems, and effective social institutions, survival for several centuries to perhaps a millennium is conceivable, though it pushes beyond anything humanity has ever achieved in terms of sustained institutional and engineering continuity. Beyond a millennium, we enter the realm of pure speculation. No human institution, no human technology, no human community has ever remained continuously functional for 1,000 years without external support. The generation ship would need to be the single most robust, resilient, and adaptive system human beings have ever created, by a wide margin, sustained across more generations than separate any modern person from the builders of medieval cathedrals. This is not a reason to abandon the idea. It is a reason to understand its true difficulty. A generation ship is not a bigger version of the International Space Station. It is not a submarine with a longer deployment. It is an attempt to build a self-sustaining civilization inside a sealed container and keep it running for longer than most civilizations on Earth have lasted. It is, without exaggeration, the most ambitious engineering, biological, and social project that human beings could ever attempt. And maybe that's the most important thing to take away from all of this. Not that it's impossible, but that it's hard. Genuinely, profoundly, almost incomprehensibly hard. The distance between the stars isn't just measured in light years. It's measured in the number of generations that must live and die inside a metal world, maintaining systems they didn't build, following a mission they didn't choose, preserving knowledge they might not value, all in the hope that their distant descendants will someday step onto a world none of them have ever seen. Think about what that actually asks of people. Not of engineers or scientists in the abstract, but of individual human beings. A child born on this ship 200 years into the voyage will open their eyes for the first time inside a metal corridor. They will never feel wind on their face unless someone built a machine to simulate it. They will never see a horizon. They will never stand in rain. They will never swim in an ocean or climb a mountain or watch a sunset, paint the sky in colors that no artificial light can replicate. Their entire world, from birth to death, will be the inside of this vessel, and they will be asked to spend their life maintaining it. To learn reactor physics not because they're curious, but because the ship dies if they don't. To accept restrictions on who they love and who they have children with. Not because they understand the genetics, but because someone tells them it's necessary. To wake up at 3 a.m. when an alarm sounds and fix a water pump. Not because they care about a destination they'll never see, but because everyone around them will die if they don't. That is an extraordinary thing to ask of a human being. And it must be asked not once, but every day. Of every person. For every generation. For centuries. The generation ship doesn't just need to survive physically. It needs to give its inhabitants a reason to keep it alive. It needs to provide meaning, purpose, something worth waking up for. something worth sacrificing for. And it needs to do this in an environment that strips away most of the sources of meaning that human beings have relied on throughout their history. Connection to nature, freedom of movement, the possibility of exploration and discovery, the hope that tomorrow might be different from today. All of these are absent on a generation ship. The ship must replace them with something, and whatever that something is, it must be durable enough to sustain people across more generations than any religion, any philosophy, any cultural tradition has ever sustained anyone on Earth. The stars are far away, but the real distance isn't the space between them, it's the time, the generations, the centuries of human endurance required to cross that space in a vessel made of metal and hope. And whether humanity ever attempts this journey, and whether we could survive it, may be the ultimate test of what our species is capable of, not just as engineers or scientists, but as a civilization, as a community of human beings who must decide together whether the stars are worth the price of reaching them. That question has no easy answer, but it may be the most important question our species will ever face. Because if we can do this, if we can build a world inside a ship and keep it alive for centuries, then we can do anything. And if we can't, then the stars, beautiful as they are, remain forever out of reach. Not because we can't cross the distance, but because we can't survive the crossing. And that, more than any number measured in light years or trillion kilometers, is the true measure of how far the stars really are. The next time you look up at the night sky and see those points of light scattered across the darkness, remember what it would actually take to reach them. Not just the engines and the fuel and the speed, but the people. The generations of people who would live and die inside a metal world, never seeing what you see right now, never feeling the air you're breathing, never standing on the ground beneath your feet. They would carry all of humanity's hopes across the void, sustained by nothing but their own endurance, and the systems their ancestors built. And the question of whether they could make it, whether any human community could hold together that long, remain that skilled, stay that committed, keep that many systems running for that many centuries, that question remains unanswered. We don't know if we could do it. We've never tried anything remotely close, but the fact that we can ask the question, that we can look up at those distant points of light and imagine the journey, that we can calculate the distances and understand the obstacles and still wonder whether someday, somehow, we might find a way that says something about what we are. We're a species that looks at the impossible and asks how. And perhaps that, more than anything else, is what would carry a generation ship across the darkness. Not the engineering, not the biology, not the governance or the genetics, but the stubborn, irrational, deeply human refusal to accept that the stars are beyond our reach. Whether that refusal is wisdom or folly, only the attempt would tell us. And maybe that's enough. Maybe the question itself is the beginning of the answer. Thank you for joining me tonight. If you found this exploration meaningful, a like or subscribe would mean a great deal. It helps this channel keep exploring these deep questions about our place in the universe and the future of our species. Sleep well tonight on this small planet, under this open sky, with the wind and the rain and the sun and the stars all around you. Because everything you take for granted, the air, the gravity, the warmth, the sheer miraculous ordinariness of standing on a living world, would be the thing a generation ship crew misses most, and what they would give anything to see again. Good night.